So today we are talking about section 1.5, which is all about exponential functions. So, while a linear function, which we have learned about the last few sections, while a linear function has a constant rate of change, which we know as the slope, right? Alright, so while a linear function has a constant rate of change, an exponential function has a constant percent, or sometimes called relative rate of change. And what we mean by that, this means that each, I'll call it step of data, depends on the previous step. Alright, it's not a constant rate, so no matter where you are, you're stepping, 3 at a time. It actually depends on your previous step, okay? And that's why we call it a relative rate of change. So, an exponential function looks like exponential functions look like f of x is equal to k times a, and a to the power of x. Alright, so we have k times a, and a is raised to the power of x. Okay, a is called the base. Alright, it's called the base of the function. And here we have the exponent, and hence where we get our term exponential function. Alright, so a new restaurant just opened. And k, by the way, this is just some constant, which we will address a little bit later. So a new restaurant just opened. The table below gives some values, f of t, for the number of guests on day t. Could f of t be exponential? Why or why not? So first of all, we know all about linear functions and how to determine if a data set is linear. Okay, and if we remember, it has to be equal changes in t, we are increasing by 1 each time, and constant changes in f. So let's figure out what these changes are. Well, from 14 to 18, we add plus 4. 18 to 24, that's plus 6. 24 to 31, plus 7. And 31 to 40, plus 9. Okay, so this tells us this is not a linear function. Not a linear function. Alright, but is it exponential? Just because it's not linear doesn't automatically tell us it's exponential. Alright, so what we need to do is test to see if there is a constant percent change. A constant percent change. Alright, so how we do that is for between the first two values, we're actually going to take 18 and divide it by 14. So up here we have t is equal to 2 divided by t is equal to 1, right? So this gives us about 1.28, and our question asks us to round to 1 decimal place, so we're going to say that's 1.3. Alright, so we have to check it again. We have to check between t is 3 and t is 2. So we have 24 divided by 18. we get 1.33, and if we're rounding to 1 decimal place, that's just 1.3. We'll go ahead and check the rest of them. So we have 31 over 24. That also rounds to 1.3, and 40 over 31, which also rounds to 1.3. Okay, so these are all relative rates of change. And if we notice, they are all equal. So because these are all equal, this data set represents an exponential function. Alright, so that is how we check to see if a table of values describes an exponential function or not. And this one is exponential. Alright, so exponential value or functions are used a lot in population dynamics. Alright, so I need some more space before our next example. Alright, typically we use P of t. Alright, and we write this, so this could be a population, right, where t is some time in whatever units given in our problem. And we're going to say that our population needs to have a beginning population, that's our P naught, so our initial population. Okay. And then multiply this by some base a to the power t. This is our exponent. Exponent and base. Alright, so this is our typical population function. P naught is our initial population value, right? And we get this when t is equal to 0. So that's one of our intercepts, right? Alright, so then we recognize that we can either have a growing population or a decreasing or decaying population. Alright, and all of that rests on the base. So, if, whoa, crazy pen, if the base A is greater than 1, we have exponential growth. Exponential growth. Okay? And if A is less than 1, we have exponential decay. Decay. Alright. And we also have a hidden in here, A is actually found by 1 plus R, where R is the rate of change. Okay, and R can be positive or negative, depending on growth or decay. Alright, and R is the, I'm going to say it's the percent rate of change. Alright, expressed as a decimal, just to be super specific. Alright, so now we can jump into example number 2 of Mildred's hat collection. Alright, in 2014 she began with 25 hats, and she plans to increase her collection 25% per year. Write a formula for h of t, the number of hats Mildred will have, t years. If I could get my thing in here. Anyways, t years after 2014. How large will her hat collection be in 2020? Okay, so let's highlight some important things here. She began with 25 hats. Well, that would be our initial, you could say it's a population of hats, or we could say amount. Initial amount of hats, well, that's going to be our P naught, is 25. She begins with 25 hats. All right, she also plans to increase her collection. So we know increase. This tells us that R should be positive. And also this tells us that A is going to be greater than 1. All right, that's everything we get from increase. Her collection by 25% per year. So 25%, that is the rate. So R is equal to, but we don't write it in terms of percent, we write it in terms of a decimal. So 25% is 0.25. Okay? So we have all of the necessary information. Well, now we need to find A, where we know A is 1 plus R. And we found R to be 0.25, so A is 1 plus 0.25. So A is 1.25. All right, that checks out. A is greater than 1, which we were expecting. So our population of hats at time t, well, it's going to be our initial population of hats. So we started with 25 hats, multiplied by our base is A, so that's 1.25, and then to the power of t. We need that exponent in there. So the final part of our problem asks, how large will her hat collection be in 2020? So we need to know, she started in 2014, so technically that's when t was equal to 0. Okay, that was our initial time. So if we want to know what her hat collection will be in 2020, that is going to be 4 years later, so t is equal to 4. Okay, so 4 years later, we have P of 4. Well, that is 25 times 1.25 raised to the 4th power. And so we get that she will have 61 hats in 2020. And that is a lot of hats. Okay, so example number 3. Make this a little bigger. There we go. So the grades of 6 students are given by the equations below, where time, t, is measured in weeks after the first midterm exam. Alright, so the first problem here, A, Alex's grade has been decreasing. Alright, decreasing since the first exam. Which formulas could represent her grade and why? Alright, so we just learned, so if we have our population is equal to our initial population times A raised to the power t, okay, we know that A greater than 1 is increasing and A less than 1 is decreasing. Okay, so we are looking for formulas in the above table that have an A that is less than 1. Alright, so let's look at equation number 1. Well, equation number 1 has A as 1.001. So that is greater than 1, so it's not number 1. Alright, let's look at number 2. Here we have A as 1.05. That is also greater than 1, so it can't be that one. Equation number 3 has A as equal to 0.9. Alright, so 3 is a contender. 4, we have 0.99, which is just barely less than 1. but also a contender. 5 has A as 1.03, so that's greater than 1. And 6 is 0.89, so 6 is also a contender. All right, so all three of these are contenders for Alex's grade because all A values are less than 1. All right, so that goes with our decreasing. All right, so which student's grade is falling the fastest? Part B. Well, let's go look at 3, 4, and 6 are the only three that are decreasing. Okay, and we're looking for the number that is furthest away from 1. All right, because if it's at 1, then it's not changing at all. And if it's over 1, then it's increasing a lot. Or then it's increasing. So if it's super close to 1, then it's decreasing, but not by a lot. And if it's an even tinier number, then it's decreasing faster. So we're looking for the smallest A value. All right, looking for smallest A value. All right, which in this case would be student number 6. All right, so student number 6. Part C, Umar's grade has been rising since the first exam. Which formulas could represent his grade and why? So similar to Part A, we're looking for all of the A values that are now greater than 1. All right, so equation number 1 has an A value greater than 1, equation number 2, and equation number 5 all have A values greater than 1. So those are all contenders. So equation number 1, equation number 2, and equation 5 all have A greater than 1, which means they are increasing. Which student's grade is rising the fastest? Well, now we're looking for the largest A value. Largest A value. Well, out of the three that are rising, it is equation number 2 that is rising the fastest. Okay. And part E, Karen came, we need an E there. Karen came out of the first exam with 85% in the class. Which formulas could represent his grade? All right, so 85% in this case is going to be our initial population, or value, would be a better word in terms of grades. So we're looking for an equation that looks something like P is equal to 85 A to some exponent. All right, because that is our initial value. So if we look at the table again, we see that equation number 4 and equation number 6 both have 85 as their initial values. So both of those are contenders for being Karen's grade. So number 4 and number 6. Okay, example 4. Suppose an investment of $800 earns 7% interest per year. We are to come up with a formula for how much money that you will have after T years. All right, so again, we're going to look at an exponential function where we have an initial value and a base raised to an exponent. So in this case, our initial value is $800. So initial value is $800. Okay, and then A is 1 plus R. We need to find out what R is. R is the rate, which is given to us as 7% interest per year. Well, again, we need this in decimals, so we have 0.07. That's our 7%. So A is then 1 plus 0.07, so we have 1.07 is our A value. So P of T is equal to 800 times 1.07 raised to the T. And so we could find out, if we wanted to know how much money we'd have in 10 years, we just need to plug in 10 for the letter T. And that is all of example 4. Moving on to example 5. Say your boss proposes 2 different plans for giving raises, and suppose that you currently earn $32,000 per year. In the first plan, you earn an additional $1,000 each year. In the second plan, you increase your salary by 3% each year. Which plan do you think is better? And then we're going to check your guess by computing the salary for 5 years and then 10 years under both plans. So take a second, think, which plan would you pick right off the bat? And then we'll see if your guess makes sense mathematically. Alright, so I'm going to say P1, alright, and then we'll have P2 over here. P1 of T and P2 of T. So under the first plan, we start with $32,000. Alright, and we earn an additional $1,000 each year. Well, that is a constant rate of change. So over here we have a linear function. So we have $32,000 plus $1,000 every year times T. Okay. And in our second function, P2, well, we also are starting out with $32,000, but now we have a percent rate. Okay, so our rate is 0.03, so A is 1 plus R, so we have 1.03. So our function is $32,000 times 1.03 raised to the T. And here we have an exponential function. Exponential function. Alright, so we need to calculate P of 5 and P of 10 in both plans. Alright, so P1 of 5 years, so this will be your salary after 5 years of raises. Well, that's just going to be $32,000 plus $1,000 times 5 years. So that's $32,000 plus $5,000. So we have $37,000. And P2 of 5, well, that's $32,000 times 1.03 raised to the 5th power. And so if we plug this into a calculator, we will end up with $37,096. Okay, so pretty comparable, right? The exponential function just gives you 96 more dollars. Okay? But what happens after 10 years? So for our first raise plan, we have P of 10 years. So we have 32,000 plus 1,000 times 10. So we end up with 32,000 plus 10,000. So we get $42,000 is now your annual salary. Okay, but if we come over here to option number 2 of 10 years, we have $32,000 times 1.03 raised to the 10th power. And again, the calculator tells us that this is $43,005. So here it's now a difference of $1,005, and it's only going to become a greater difference from there. So the exponential function, so the second option would be the better option. You would get a higher salary in the end. Okay. Example 6. Write an equation for each of the exponential functions whose graphs are shown below. Alright, so in each of these situations, we are given 2 points, and we need to come up with an equation for the exponential function based on the 2 points. We can do that for a linear function. We've been able to find the slope and then plug it into our function or our equation of a line. And so now we're going to do a similar thing with exponential functions. So let's look at graph A. So we need to come up with what are the 2 points we have in graph A. Well, they're labeled here, but I'll draw them in big bright red. Okay, our first point, well, x is 0 and y is 100. Okay. And our second point, x is 3 and y is given as 21.6. So the way that we are going to find an equation is we're actually going to solve 2 equations at the same time. And so what we're going to do is use this equation, y is equal to a times b to the exponent, and we're going to plug in values from given points. Because what we need to know is we need to find a and b. Okay? We know y and we know x, and so we need to use them to find a and b. So we're actually going to do 2 different equations. So I'm going to call this y1 is equal to a times b to the power of x1, and then y2 is equal to a times b to the power of x2. And then pick either point you want and label them x1, y1, x2, y2. Okay, so now I'm going to plug in these points. So for y1, I have 100, a times b, and x1 is 0. And anything to the 0 power is 1. So I just end up getting that a is equal to 100. Okay, that was pretty simple. And for y2, I have 21.6 is equal to a times b raised to the x2, so that's 3rd power. Okay, but I now know what a is. So I can plug a into this equation to get 21.6 is equal to 100 times b cubed. So we can go ahead and divide both sides by 100, which really just moves our decimal over twice. So we end up with 0.216 is equal to b cubed. And then if I take the cubed root of both sides, I will end up with 0.6 is equal to b. So I found A, I found B. Those were the two values that I said earlier we needed to find. So our equation for graph A is going to be y is equal to 100 times 0.6 raised to the x. And there we go. That is our equation for the function. So we're going to do the same thing with graph B. So the 2 points given here are 2 and 92.5 and 0 and 32. Okay, real quick, I wanted to mention this about part A. We notice that our base is less than 1, which means we have a decreasing function. And if we just look at our graph, we definitely are decreasing, so that checks out. Again, just making sure we didn't throw any red flags. All right, back to part B. So we graphed those 2 points, so now we're going to do the exact same thing of solving 2 equations. So for part B, we have the points 0 and 32, and 2 and 92.5. Label them x1, y1, x2, y2. I like to label everything just to keep it super clear in my brain. Otherwise, I will definitely use x1 with y2 instead of y1. And so it's just helpful for me, and hopefully it'll be helpful for you as well. So again, we're going to be using the formula y is equal to ab to the x. So we have y1, which is 32, is equal to a times b raised to x1, which is 0. Again, anything to the 0th power is 1, and so we end up with 32 is equal to a. Okay, and then over here we have y2, which is 92.5, is equal to a times b raised to the 2nd power. But we now know that a is 32, so we get 92.5 is equal to 32 b squared. And then we can go ahead and divide by 32. So we'll end up with 2.89 is equal to b squared. And then we can square root both sides to get b is equal to 1.7. Alright, so we have found a and we have found b. And technically b should be positive or negative because of the square root. However, we notice that our function is increasing, so we want it to be positive and greater than 1. Okay, so our function is y is equal to 32 times 1, whoa, crazy pen, 1.7 raised to the x. And that is our equation for graph B. Next we have graph C. Let's see, where these 2 points are -2 and 9.5, and 1 and 0.5. Okay, and again we are decreasing, so we're looking for a base value smaller than 1. So graph C, our points are -2 and 9.5, and 1 and 0.5. Again, x1, y1, x2, y2. Go ahead, take a minute for yourself and see if you can do these calculations on your own, and then tune back in to see if you can get them right. So y1 is 9.5, it's a 9. is equal to ab to the negative 2. And I'm going to go ahead and solve this for a. So the last two problems, we had b raised to the 0th power, and that was very convenient because then it just went away. Unfortunately, that is not always the case. So here, I'm going to go ahead and multiply by b squared on both sides, because technically b to the negative 2, that's the same thing as 1 over b squared, if we remember our exponent rules. Negative exponent just means switch it to the top or the bottom, wherever it is not currently. Okay, so if I multiply this by b squared, it's going to cancel out. Okay, so if I multiply both sides by b squared, I'll end up with 9.5. b squared is equal to a. So I've technically solved for a by now. So I can come over here to our next set of data points and say that 0.5 is equal to ab to the first power. Okay, so then I'm also going to multiply here by a b to the negative 1 to move the b over. Technically, I'm dividing by b. So what I've done here is solve for a in both equations, which means I can now set these equal. Set equal. So I have 9.5 b squared is equal to 0.5 b to the negative 1. So I'm going to go ahead and multiply by b to both sides again to cancel out this b to the negative 1. So I'll get 9.5. This time I'll have b cubed is equal to 0.5. All right. And then I'm going to divide both sides by 9.5. So we'll get b cubed is 0.5. Cubed is 0.052. And then we need to go ahead and take the cubed root of both sides. So this, we end up with b is equal to 0.37. All right, so we found b, but remember we had a in terms of b over here. So we still need to calculate a real quick. I'll come over here. So now we have 9.5, 0.37 squared is equal to a. And so we get that a is equal to 1.3. So our function is y is equal to 1.3 times 0.37 raised to the x. And that is our final equation for the third graph. All right, example number 7, and this is our last one for today. Suppose a city has a population of 400,000 at time t is equal to 0, where t is the number of years after 1990. All right, there's supposed to be a space there. Part A says if the city's population decreases by 2,500 people per year, find a formula for P of t, the city's population, t years after 1990. I'm going to give you a second to think about the wording of this question. We have just spent a whole section talking about exponential functions, and so immediately you're probably thinking, okay, exponential function. However, read it carefully. We have a decrease of 2,500 people per year. That is telling us we have a constant rate of change. Does that describe an exponential function? Or does that describe a linear function? when I first did this problem, I started trying to do an exponential problem, or exponential function, and I was like, why is this not working? All right, so make sure you're reading the questions very carefully and making sure you're getting all of the hints that are in the wording. So, our population function is still a function of t, and we still know that we need to start out with 400,000 people, but now we know we're looking for a linear function. And we have our slope, we have our rate of change is 2,500. We know it's negative because we are decreasing. And per year, so we just need to multiply that by t. And that is our equation. Okay, so part B says, what if the city's population decreases by 6% per year? Well, there we have it. We so badly wanted to use an exponential function in part A, and here we get to in part B. So this is the exponential version. Exponential function. Okay, so our rate is 6%, so that's 0.06. We know we are decreasing, so it's got to be negative. So A is 1 minus 0.06. So our A value is 0.94. That's our A value. And our initial population is the same. It's still 400,000. So now we can write our population function of time. Well, we're starting out with 400,000 is our initial population, multiplied by 0.94 and raised to t for how many years after 1990, and that is our answer for part B. So that was the last example for section 1.5. Please email me with any questions, and don't forget the comprehension quiz.